Okay, so today we're going to be talking about D2. This is the next section of Astrophysics unit. Um, this is called Stellar Characteristics and Stellar Evolution. And this is just to give you an idea of what we're going to be talking about in D2. We're going to be talking about things like stellar spectra and Hertzsprung-Russell diagrams today. In the next video, we'll probably talk about mass-luminosity relation for main sequence stars and Cepheid variables. And then in the last video or two, we'll talk about stellar evolution, how that pertains to HR diagrams. We'll talk about what is a red giant, what is a white dwarf, neutron stars, black holes, and the Chandrasekhar and the Oppenheimer-Volkoff limits. And again, those have to do with stellar evolutions, and we'll talk about that not in the next video, but probably the video after that. So first we're going to talk about classifying stars and stellar spectra. And so obviously we've been looking at stars for a long time. For thousands of years, people have been looking up at the stars. And as technology kind of developed, we had the capability to classify stars in different ways. And so this is called spectral classification. So how do you categorize stars, or how do you classify stars? And so there's a few different ways you can do that. You can do that based off of, looking at the absorption lines in their spectra. We talked about atomic spectra last year, how, different elements have different characteristic, kind of like fingerprint spectra. You can go based off of their color. You can go based off of their temperature and luminosity. And so eventually we started to make some connections between what we can directly observe. For example, we can directly observe by looking at a star. We can look at its black body curve, and from that we can use things like Wien's law to find the peak, or not the peak wavelength, but the temperature. We can observe the peak wavelength, and we can also look at the spectra and notice the strength of hydrogen absorption lines. And we can use that to find out some information about the stars. And so we can use those things that are called observables to make inferences or to make calculations to determine things we can't directly measure. For example, you cannot directly measure the temperature of a star, but you can directly measure the black body curve from a star just by looking at the light it gives off and making a plot of the wavelength of that light versus the intensity. And assuming it's a black body, you can use Wien's law to find its temperature, its absolute temperature in Kelvin. You can, indirectly measure luminosity by directly measuring apparent brightness, that is an observable, and then using the apparent brightness equation, like we talked about in the last video, to find luminosity. And so let's talk about something that we can directly measure besides the black body curve, is stellar spectra. So last year in topic 7, we talked about atomic spectra. We talked about things like absorption and emission spectra and how these are created when electrons and atoms transition to different energy levels. And you can use the information from the atomic spectra of stars to find out lots of useful information about that star. For example, chemical composition, because every single chemical on the periodic table has a unique set of spectral lines. You can find the surface temperature using Wien's law, like we talked about before. You can even find information about how fast the star is moving towards us or away from us, or how fast it's rotating. And we're not going to get into that now, but it can be done. And so when you take the light from stars and you put it through a spectrometer, remember that's the device that breaks the light given off by an object into its individual wavelengths. We can look at that pattern and figure out, what are stars made of. And based off of the observations we've made, we've seen that light of all frequencies is passing through an outer layer of gas. And basically we get something that looks like this. Now, this is not an emission spectra, this is an absorption spectra. Okay. Remember, the difference is an emission spectra, it comes off something that is just emitting light at those frequencies, whereas an absorption spectra is what you get when you take white light, which has all frequencies, and you pass it through a gas. And when we look at the spectra of stars, we see something that looks like this. Now, what that tells us is that basically the light coming from a star is generated by white light, or light of all frequencies, passing through a gaseous layer around the outside of the star. Okay, which kind of makes sense because that's why we treat stars as black bodies, because they emit light at all frequencies. And of course, by looking at the lines, we figured out that basically all stars are made of hydrogen and maybe some other elements. So here is an example of some different spectra for different stars, and not every star looks the same. If we look at the spectra for some stars, we see they have more red. If we look at spectra from other stars, we see they have maybe more blue or more violet. And so this gives us a way to classify stars based off of the lines that we see and the relative intensity of the different lines. So one way you can classify stars is using a system that looks like this. Okay, this is the OBAFGK MLT classification system, and luckily you don't need to memorize that. It used to be part of the IB curriculum, but they don't make you memorize the order or anything like that. But basically this is just to give you an idea that there's different ways to classify stars. Now if you look at the order, it doesn't go in alphabetical order. The way it's listed on this chart is actually from the highest temperature down to the lowest temperature. Okay, so if we look at what we now call a class O star, if we look at the atomic spectra, or not the atomic spectra, the stellar spectra, we see ionized and neutral helium in the spectra, as well as like weakened hydrogen lines. Those stars tend to correspond to blue stars with very, very high temperatures. Okay, and the reason we see things like, lots of helium, ionized helium, less hydrogen, is because those stars are so hot that they basically ionize the hydrogen completely. As we go down, we get cooler and cooler stars. You can see that the hottest stars tend to be blue. The coldest stars tend to be reddish. Okay, our sun is probably somewhere here in this region. I believe we're a class G star. Again, you don't need to know any of the details on this slide other than to know that this is one way to classify stars based off of the temperature or the color, and we can infer those things based off of the spectra, which we can directly observe. Okay, so we've talked about spectra before. Like I said, we can use those to find the chemical composition of a substance because each individual element on the periodic table has a unique set of spectral lines. And based off of our observations of many different stars from Earth, we see that most stars have all or some of the hydrogen lines, indicating that stars tend to be made of hydrogen. Now, some stars are made of completely hydrogen, some have other elements in them. Some hotter stars have no hydrogen lines because, I said this on the last slide, they're so hot that all the hydrogen has become ionized. And other elements can be detected like calcium or helium or oxygen or neon in the really big stars. And again, these are things we can directly measure. We can look at a star and put the light coming from the star through a spectrometer and get something like this. And again, it's almost like a barcode that tells us all this information about the stars. Okay, now the last thing it says on here is by making measurements of star luminosity and temperature, we can begin to notice certain trends. And so this brings up the idea of what we call HR diagrams. Okay, HR diagram is named after the two guys who basically came up with this idea, Hertzsprung and Russell. So Hertzsprung and Russell came up with the Hertzsprung-Russell diagrams. We don't like to say that because it takes too long to say, so we call them HR diagrams. And basically it's a way of plotting a bunch of stars in a way where we can start to see patterns. Okay, so typically on an HR diagram, on the x-axis, you have temperature. Now, be aware that this typically goes from the highest temperature on the left side to the lowest temperature on the right side. On the next slide, I'll show you like a blown up picture of this so you can see. But over here we have like 30,000 Kelvin. Over here we have 3,000 Kelvin. On the y-axis, you have the luminosity of stars relative to our suns. Now, it's very important that you understand what that means, relative to our suns. So, if you take a look at this blown-up picture, you'll see, for example, that our sun is right here. Okay, and I'm going to draw a horizontal line. Actually, maybe choose a color that you can see a little bit better. Okay, I'm going to draw a horizontal line like this. And what you should see is that our sun has a relative luminosity of 1. Now, does that mean that L equals 1? No, of course not. The luminosity of our sun is a way, way bigger number than that. What that does mean is that the luminosity is 1 times the luminosity of our sun. Remember, we use this little symbol to represent the luminosity of our sun. And I forget what the number is. It's like 3 times 10 to the 26 watts or something like that. And so on the y-axis, we have these numbers. These are in terms of our sun's luminosity. So for example, the star right here doesn't have a luminosity of 10 to the 3, but this star right here would have a luminosity of 10 to the 3 times the luminosity of our sun. Now that's not, the value of the luminosity of our sun is not a value that you need to memorize or anything. You'd typically be given that in a problem. Again, I don't remember the exact value. I know it's something like 10 to the 26 watts or something like that. So make sure that you're very aware that these are all measured relative to our sun's luminosity. Also be aware, I'm going to erase this, so pause it here if you need to look at this. Also be aware of the other thing I said, that the temperature tends to decrease from left to right. And so the stars that are hottest tend to be over here, and the stars that are coldest tend to be over here. Now, going back to the last slide for just a moment. The other thing I want to point out is that by making observations of many, many different stars, we start to see that they fall into kind of patterns. Okay, so let me identify the patterns for you. So here, in case you cannot see, we have the white dwarfs. Okay, we'll talk about what white dwarfs are later on. But those are stars that tend to be relatively low luminosity, but relatively high temperature. This band right here, okay, that I'm drawing the green line through right now, this is what's called the main sequence. Okay, the vast majority of stars fall along the main sequence. Up here we have red giants, and then we have supergiants, which may or may not be red based off of their temperature. Of course, hotter stars tend to be more bluish. Okay, and so those are the typical trends you see when you make an HR diagram plot. And again, this is based off of observations of many, many different stars. We measure the temperature and the luminosity using methods that we've talked about before. And if you make enough observations and you plot them, then you get these general trends. And again, we haven't talked about what a giant is, or what a white dwarf is, or what a main sequence star is, but we'll get to that later. Okay, so this is the general form of an HR diagram. You definitely need to be able to label this type of diagram and know what the different parts are. Okay, and also notice if you look closely, it has lifetime information on here. Okay, this is 10 to the 7 years versus 10 to the 11 years. Okay, so another general trend that you need to be aware of is that typically stars that are smaller, that is, stars that have less mass, typically tend to live longer, whereas the biggest, hottest stars in the universe tend to die very quickly. 10 to the 7 years is only 10 million years, right? That's not long at all. Our sun is probably a couple billion years old. And so basically, you can think of these stars up here. These are kind of like the rock stars of the universe. They burn really hot, and they they burn out really quickly, just like rock stars. Whereas these are like the cooler, longer living stars. Okay, so because they're not as hot, they tend to last a lot longer. Even though they have less mass, they don't burn through it as quickly. And basically the reason for that is because the more mass you have, the more everything is compressed, the higher the rate of fusion is. And the higher the rate of fusion, the more you use up that fuel. And so the faster the star dies. Okay, so I'm going to erase this. Okay, the next few slides just kind of go through the HR diagram some more. The stars are not randomly distributed. There's 3 features. You have the main sequence, kind of following along a strip from left to right. some large stars, like the red giants, tend to be up here, and the bottom left is a region known as white dwarfs. Those are small and hot stars. And again, we'll talk about how those different types of stars form. Our sun is a main sequence star. The vast majority of stars are main sequence stars. And in fact, basically any star that forms at some point is a main sequence star. But we'll talk more about stellar evolution later. Although you should be aware, I'm just going to go through these. These are basically all just examples of HR diagrams. None of them are really new or anything. They're just different formats of the same thing. So just some general details about the different types of groups. And again, we'll go into much more detail about this later. But main sequence stars are stars that fuse hydrogen into helium. Now, at some point in the star's lifetime, it runs out of hydrogen, and so it stops being a main sequence star, and it becomes something else. And so something else you need to be aware of is that a star's position on an HR diagram is not fixed. For example, our sun is currently a main sequence star, and you can see it right here. But at some point in our sun's lifetime, it is going to expand and become a giant. And then after it goes through its giant phase, it's going to end up as a white dwarf. Okay, and so you should realize that any given star's position on the HR diagram is not something that's fixed. Stars can evolve over time and change their position on the HR diagram. Okay, just like our sun is going to do. And we'll talk about stellar evolution later, but the path it takes on the HR diagram kind of depends on the mass of the star to begin with. Some stars, like our sun, are relatively small, and they just become giants and then end up as white dwarfs. Other stars can die in a more spectacular way, like supernovas, and they can become black holes or neutron stars, stuff like that. And again, we'll talk about that later. Okay, but you should know that a star's position on the HR diagram is not fixed. Let's see, what else do you need to know? White dwarfs are the end result of a small mass star. Giants are a star in between main sequence, and white dwarfs for smaller stars like our sun is going to go off the main sequence, become a red giant at some point in a couple billion years, and then end up as a white dwarf. And then supergiants are the result of a high mass star ending its time on the main sequence. And again, we'll talk about stellar evolution at the end of D2. Let's see. And I mentioned the first bullet point already. You should realize that the star's position on the HR diagram might change. Notice that this HR diagram reflects what we should realize from the Stefan Boltzmann law, that star's luminosity increases with temperature and or size. Okay, so in other words, the stars with the highest luminosity tend to be either the biggest in the case of these red giants, or the hottest in the case of these blue stars, or both. Okay, you have some stars that are very big and very hot, which is why they have a high luminosity. Okay, so if you think of the Stefan Boltzmann law, right, we have L equals sigma A T to the 4. There's two ways you can increase the star's luminosity, either by having it at a higher temperature, that is, on the left side of this diagram, or if the surface area is bigger. Remember, this is 4 pi r squared in the equation. If you have a bigger star, it's also more luminous. Okay, and so that's why if you look at the top part of this graph, all these stars either are very big or very hot, or both. Okay, and again, that's just what you would expect from understanding Stefan Boltzmann law. Okay, so by observing a star, we can determine its blackbody curve and therefore its temperature from Blind's displacement law. We've talked about that before. And then by assuming the star is the main sequence star, we can use the HR diagram to estimate the luminosity of the star. And that's something we might talk about a little bit later. The last thing we're going to talk about in this video, just really quickly, this is showing how a star might possibly change its position on the HR diagram over time. And again, you don't need to know what any of these things mean. We'll talk about stellar evolution later, but this is basically what's going to happen to our sun. It's eventually going to become a subgiant, and then a red giant. It's going to give off a planetary nebula where it's glowing really brightly, and then the core is going to become a white dwarf and eventually end up down here off of the main sequence. Okay, so again, the star's position on the HR diagram is not fixed. So hopefully that clarifies the first couple pages in the notes as far as D2 goes. We're going to have another crash course video which hopefully fills in the gaps. I would definitely recommend that you read the first few pages of your textbook over D2. In the next video, we're going to talk more about Cepheid variables and the mass-luminosity relationship, and we'll get into some calculations and stuff like that. Okay, but it's important that you understand what the HR diagram is and about how to classify the different parts of the HR diagram and be able to draw where a star should fall if given its properties, high mass star versus low mass star. And that's something you'll be able to do later on when we talk about the different paths of stellar evolution. So let me know if you have any questions.